Hello to everyone who watching. So we are Group A here. Today we will be presenting our design of the booking system. So I'm the speaker Lee Sun Jae, and these are my teammates Arif, Weihan, and Amos. So we will begin with lecturer's perspective, which is time slots, attributes, and booking lists. So we will be defining a struct array called lecturer. So each lecturer will hold lecturer name in string format, total hours representing the total accumulated hours is in double format, and also there will be the pointer for lecturer, and the pointer will be pointing to its booking slots. So like I mentioned just now, each lecturer holds a pointer for a linked list. So basically the linked list is called booking list. It's a single linked list that held by each lecturer. So each of the book lists will hold student names, appointment date, and appointment time. So how the time slot can be modified by the lecturer. So they can be categorized to two parts, which is manually and automatically. So in manually, the lecturer can insert, delete, and edit the time slot themselves based on their free time. So they can like set up their appointment with their own. So as for the automatically part, content sort remove based on date and time, which means that the slots, once it is inserted into the linked list, it will be sort automatically to the right position according to date and time, and same as the remove functions, it will be removed once the time or date has been passed. So all this is done by singly linked list and the queue, and also the sorting is called binary sort. It will be explained by Amos in the later slides.
Hello, I'm Weihan, and I'll be in charge of the student part of this presentation. So we decided to use two linked lists in total for the student part. The first linked list is so that we can store student details such as their student name and student ID. As to why we use the linked list is because we don't know how many students will decide to book slots in like a week. The second linked list is because we also don't know how many like time periods that the students will book. That's why it's also linked list. As to why both are in queue is because we need access to the earliest data that was stored in the linked list. So there will be two ways to manually interact with the slots. One is by choosing the slots, and the second one is to delete the slots. Each slot will be sorted automatically by date and then by time. And same, and also automatically the slots will be deleted once the current time has passed the slot time. And that is all for the student part. Thank you.
Hello, I am Arif and I will be presenting the management side of the assignment. So, as we all know, the assignment stated that the system for the management side will view the total number of consultation hours for each lecturer that has accumulated for the semester. Now, how do we sort the consultation hours inside the system? The consultation hours for each lecturer will be sorted automatically according to the total consultation hours. We are using single linked list and stack for the management system, and we will also be using binary sort for the sorting process. Now, the attributes for the management system are lecturer name and total hours, which are labeled as lec name and total hours. As you can see, this is a brief look at the structure of the management system that we will begin to develop soon. Now, I will pass over the mic to my next groupmate. Thanks.
Hello guys, yes, I'm gonna be doing the searching and sorting algorithms. So first of all and foremost, we're gonna be starting with the sorting algorithms. Yeah, so my first sorting algorithm is insertion sort. This is a in-place comparison based on sorting algorithm. Hence, here a sublist maintained which always sorted. For example, the lower part of an array is maintained to be sorted, and an element which is to be inserted in the sorted sublist is to find its appropriate place, and then it is to be inserted there. Hence, the name insert sort. The array is searched essentially, and unsorted items are moved and inserted into the sorted sublist in the same array. This algorithm is not suitable for large data. It sets as its average and worst case complexity. For example, it is like n to the power 2, where n is the number of items. That's what it is. Then the characteristics is shown on the slides. This algorithm is one of the simplest algorithm with implementation. As you can see, basically insertion sort is efficient for small data values. Insertion sort is adaptive in nature, i.e. appropriate for data sets which are already partially sorted. As you can see here, self-explanatory. So we're gonna be working on the insertion sort on our project. We are about to make the program of the thing we're gonna make in the next few weeks for the assignment. How insertion set works: we take an assorted array. For example, these are the numbers 14, 33, 27, 10, and others. Insert sort compares the first two elements. You compare the first two elements, then you go under, then it finds both 14 and 33 are all in ascending order. For now, 14 is sorted sub list, as you can see here. Insertion sort moves ahead and compares 33 with 27, and it finds 33 is not correct, is not in the correct position. Then 33 swaps with 27, and it also checks in small elements sorted sub list. Yeah, we see that the sorted sublist is only one element, 14 and 27, right? Is 14 right? And 27 is greater than 14. Hence, the sorted sublist remains sorted, as you can see after swapping. By now we have 14, 27 in sorted sublist, as you can see. Next, we compare 33 with the next number, the next value. We compare it with 10. Then we see 10 is what? Is 33 is greater than 10. So the values are not in the sorted order. So we then swap. We swap again, right? However, swapping makes 27 and 10 unsorted, as you can see, because there's 14 here, right? As you can see, 27 and 10, they are not sorted now. Hence, we swap them too. After swapping 27 and 10, again we find 14 and 10 are in an unsorted order. Then we swap them again. By the end of the third iteration, we have a sorted sub list of 4 items, as you can see: 10, 14, 27, and 33. This process will go on until unsorted values are covered in sorted sublists, as you can see. Yeah. So I'm gonna move on to the next sort algorithm, which is selection sort. We're gonna be working with these two, so we're gonna see which one is appropriate for where we wanna work with, as you can see. So we're gonna use selection sort 2. Selection sort is a simple sorting algorithm. This sorting algorithm is in place comparison based on algorithm, in which the list is divided into 2 parts. The list is divided into 2 parts, right? The sorted part at the left end and the unsorted part at the right end. Initially, the sorted part is empty and the unsorted part is the entire list. The smallest element is selected from unsorted array and swapped with the leftmost element and that element becomes a part of sorted array. This process continues, moving unsorted array boundary by one element to the right. This algorithm is not suitable for large data sets or large numbers. As you can see, it is average and worst case complexities of 0 by n squared, where n is number of what? Items again. Then we move on to how it works. Consider the following depicted array, for example, right? The array. For example, for the first position in the sorted list, the whole list is scanned sequentially. The first position where 14 is stored presently. We search the whole list and find that 10 is the lowest value. As you can see, 10 is the lowest value. So we replace 10 with 14. After one iteration, 10, which appears to be a minimum value in the list, appears in the first position of the sorted list. As you can see, right, appears in the first position of the sorted list. For the second position, where 33 is residing, we start scanning the rest of the list in the linear manner. We search. We find that 14 is the second lowest value, so as you can see, in the list, and it should appear at the second place, right? We swap the value is 33 and what? And 14. Then next, after 2 iterations, the lowest values are positioned at the beginning in a sorted manner. The same process is implied to the rest of the items in the array. Then it continues until the whole thing is sorted. Following a pictorial demonstration of entire sorting process, you can just check how it goes, and it will end up like this, where it is sorted, where it's 10, 19, 27, 33, 35, 42, and 44. You see, then it's sorted, right? Then we move on to merge sort. Merge sort is a sorting technique based on divided and conquer technique. With worst case time complexity being n log n, it is one of the most respected algorithms. Merge sort first divides the array into 2 equal halves and combines them in a sorted manner. Merge sort keeps on dividing the list into equal halves until it can no more be divided by the definition. If it is only one element in the list, it is sorted. Then merge sort combines the smaller sorted list, keeping the new list sorted too. This is a difficult technique. It is difficult to work with. You just see how it works, but it's difficult. We work on that too. How it works. To understand merge sort, we take an unsorted array as follows. As you can see, we know that merge sort first divides the whole array iteratively into 2 halves unless the atomic values are achieved. We see here that the array of 8 items is divided into 2 arrays of 4 items, of 4, right, of size 4. Yeah, as you can see, this does not change the sequence of appearance of items in original. Now those 2 items with size 4, right, the arrays, they are then divided again into halves, as you can see. So we now have 4 arrays of size 2, as you can see. Yeah, we further divide these arrays and we achieve atomic value which can no more be divided. So they are further divided to a state that they can no more be divided, where they are size of 1, as you can see on the last part, 14, 33, 27, 10, 35, 19, 42, 44, as you can see. That's how it happens. Now we combine them in exactly the same manner as they were broken down, as you can see. Please note the color codes given of these lists. We first compare the element of each list and then combine into another list in a sorted manner. We see that 14 and 33 are in the sorted position, as you can see. We compare 27 and 10, and in the target list of two values, we put 10 first, followed by 27. You see, right? We change the order of 19 and 35, whereas 42 and 44 placed sequentially. In the next iteration of combining phase, we compare lists of two data values and merge them into a list of found data values, placing all in sorted order. As you can see, 10, 14, 27, 33, they are now in sorting order. After the final merging to the list should look like this. As you can see, 10, 14, 19, 27 after the final merging, because the numbers have been sorted already. Then we move on to the next slide. So I'm finished with our sort algorithms. Then we move on to our searching algorithms. We're gonna work with the first search we're gonna use is linear search. It is very simple. It's a simple algorithm, and linear search is a very simple algorithm. In this type of search, a sequential search is made over all items one by one. Every item is checked, and if a match is found, then a particular item is returned. Otherwise, the search continues till the end of the data collection. So it moves, checking, moves while it's checking, as it says here. This is so self-explanatory, right? Means that it moves from the first, if the number, there are mixed up numbers, it moves checking the numbers. If there is 10, if it's not the lowest, it moves until it finds the lowest of them, and then it puts it to the first position. Then it goes sequentially as that. So self-explanatory. Then I move on to binary search. Binary search is a fast search algorithm with runtime complexity of log n. As you can see, it is log n. This search algorithm works on a principle, as you can see, works on a principle of divide and conquer. For this algorithm to work properly, the data collected should be in sorted form. As you can see, it should be in a sorted form. Binary search looks for a particular item by comparing the midmost item of the collection. If a match occurs, then the index of the item is returned. If the middle item is greater than the item, then the item is searched in a subarray to the left of the middle item. Otherwise, the item is searched for in the subarray to the right of the middle item. This process continues on the subarray as well until the size of the subarray reduces to 0. So I think you can understand this, but it's kind of, binary search is kind of complicated and unorganized, as you can see, unorganized data sets and everything, but I'm gonna work with that. This is how it works for binary search. For binary search, for binary search to work, it is mandatory for the target array to be sorted. So we shall learn the process of binary search, which is a pictorial example. The following is our sorted array, and let us assume that we need to search the location of value 31 using binary search. So you can see this binary. first, as you can see, sorry, in array form, 0 1 what. Then first shall determine half of what, of the array by using the formula what, mid is equal to low plus high minus low divided by 2. Yeah, this quick math. Here it is 0 plus 9 minus 2. Then you can see that's the middle value. So 4 is the what, the mid of the array where 27 lies, as you can see, 4.5 here. Now we compare the values stored at the location 4 with the values being searched. We are searching for 31, remember. Find the value at location 4 is 27, which is not a match. As the value is greater than what, 27, we have to sort. We have a sorted array, so we also know that the target value must be in upper portion of the array. So it must be in the upper portion of the what, of the array, because it's greater than the middle part number. So we change our low to mid plus 1 and find the new value again. So we change it, we plus 1, then what, we find it, so our new mid value is now on what, on 7. We compare the value sorted on location what, 7 by 31. Yeah, then the value at location 7 is not a match, rather it is more than what we are looking for. So the value must be in what, lower part portion of this location, right? Yeah, as you can see, we move on. So the value is on the lower part of the from this location. Hence we calculate the mid again. This time it is 5. Since it is 5, we compare the value sorted at location 5 to our target. We find that it is a match. If it is a match, we conclude that the target value 31 is stored at location 5. The binary search halves the search items and thus reduces the count of what, of comparisons to be made to very less numbers. So I think you understand that. This brings us to the end of our search and sort algorithms we're gonna use on our upcoming project. So yeah, that's it. Thank you.